This is lecture number 7 in the respiratory system, and in this video we want to look at this idea of partial pressure. And so once we understand partial pressure, we'll look at the partial pressure of the major gases in the environment, as well as the approximate percentage of each of those. And then we want to look at a few different ways to interfere with partial pressure of oxygen in the lungs. So PO2 is just kind of a shorthand way of saying partial pressure of oxygen. All right, so just to kind of get us thinking in the right direction, I want to come back to this. And we don't need to rehash Boyle's law. And again, you've seen this slide before, and you know what it means. It means that if you compress a chamber, then as you compress the chamber, the pressure is going to go up. Okay, so we know that. If you decrease the volume of the chamber, then the pressure is going to go down. Okay, the point is not that necessarily here. I just want to show you this picture, because I want you to look at these little red dots. Let's say that these little red dots represent some molecule of gas, and let's just call it oxygen. So these are little red dots that represent oxygen here. And so what these arrows are showing you, it's showing you that these little red dots, these oxygen molecules are kind of, they have a little bit of a motion to them, and they're moving around, and there's a whole bunch of collisions that occur, and as those happen, those are what really are ending up to being the primary determinant of pressure. So the pressure here is 100 millimeters of mercury. Okay, fine, whatever. When we go to the next slide, we see that as those collisions increase, not the next slide, the next image here, as those collisions increase, that increases pressure. Now, again, the key thing here is not so much volume changes. The key thing here is that when that gas is in this chamber, it's going to exert a certain amount of pressure. So that gas is the thing that's going to exert pressure. So if we just take that and kind of blow it up to look something like this, what we have here, I just put a little chamber here, and I'm saying that actually this big gray chamber, it's not so much chamber, ultimately it's meant to represent the atmosphere, but just for kind of a cognitive convenience, I'm just going to call this a chamber. And so what I have here is a whole bunch of oxygen molecules, and again, they're all kind of swimming around, doing whatever they do, and floating around, I should say, not really swimming around, and just like we saw over here in this picture. And then what ends up happening is that's it, right? They end up making collisions and stuff like that. But anyway, there's a certain amount of pressure that this oxygen will exert. Then if we take something like this, now I'm going to say nitrogen. Let's call these little green dots nitrogen. Nitrogen is doing the same thing. So there's a certain nitrogen pressure here. To say it differently, there's an oxygen pressure here, and then there's a nitrogen pressure here. Now, if we just combine the two, it's going to look something like this. Now, right off the bat, you see tons of nitrogen and some oxygen, and these guys are all swimming around, and there's a certain amount of pressure that they exert. So here's the thing then. The question that we have to ask is, great. Before we ask the question, I'm going to give you a fact, and the fact is the pressure in this, quote, room is 760 millimeters of mercury. Okay, that is the pressure within this quote room. Okay, and again, this room is going to represent the environment to us. So that's the total pressure. The question then becomes, which gases are contributing to that total pressure? And you know, if you're looking at the slide and you've been tracking with me, then you'd say, well, I guess oxygen and nitrogen, right? Yeah, because those are the only two gases that I've shown you thus far. The only two gases I've shown you are nitrogen and oxygen. So nitrogen contributes to some of that 760, and then oxygen contributes to some of that 760. The question then becomes, which gas contributes more to 760? And if you look at that, if you just kind of use some sense of intuition, you might say, well, I mean, there's a lot more nitrogen, it looks like, than there is oxygen. And so I guess nitrogen would contribute more to this, and you would be correct. So let's look at this table. When you look at this table, this is showing you gases in the air and their partial pressures. So which gases do we care about out there in the atmosphere? So there's a handful out there, but most of the gases are actually nitrogen. So nitrogen comprises 78.6% of the gases out there in the atmosphere at sea level. Oxygen itself comprises 20.9% of the gases out there at sea level. And then there's a little bit of carbon dioxide out there, a little bit of water out there, water vapor, and so those are also going to contribute. So these are the gases out there in the atmosphere. Again, just in the air that you breathe when you're walking outside or in your room as you're watching this video. So when you look at these approximate percentages, again, there's no way to know that. The people that measure this stuff, the people that look at this stuff in detail, they're the ones who came up with these figures. However they end up measuring nitrogen, however they end up measuring oxygen, that's not really within the domain of anatomy and physiology, but it's information that we need. So we say, okay, great. Those are the approximate percentages of nitrogen and oxygen out there. So each of those contributes a little bit of pressure. Remember the picture that I just showed you. Which gas contributes more? Well, if there's more nitrogen, then what's going to happen? If 78.6% of the gases out there are nitrogen, then nitrogen is going to account for 78.6% of that 760 millimeters of mercury. So if you take 760 millimeters of mercury, multiply that by 0.786, the number you ought to get is 597. Therefore, the partial pressure of nitrogen in the atmosphere is 597 millimeters of mercury. To say it differently, nitrogen's contribution to the total atmospheric pressure is about 78.6%. 78.6% of 760. This is the given. This is what people have told us, right? Non-A&P people have told us that atmospheric pressure is 760. If that's the case, then we know, if you just do the math out, that's about 597 millimeters of mercury. All right, great. There's nitrogen. Now, right off the bat, for those of you who are not a big fan of numbers, you might be thinking, oh man, what am I supposed to do with these numbers? Well, the good news is with nitrogen, nothing. You don't need to memorize that number. You just need to be aware that it is a big number. Let's look at oxygen, because obviously in the respiratory system, oxygen is the thing that we care about, right? Oxygen is the gas that's transported in the blood. Oxygen is the thing that binds to hemoglobin. Oxygen is the thing that's used to run run the electron transport chain. And so oxygen is what we care about. So you want to know that 21%, I'm rounding here, 21% of the gases out there in the atmosphere are oxygen. That I want you to know. You must know that. Now, I'm not so interested in trying to split hairs and say, is it how much oxygen is out there? Is it A, 21% of atmospheric gases, B, 22%, C, 23%, D, 20%? No. I don't care about that. I care that you know that it's about 21%, and it's not 10%, and it's not 90% of the gases out there. So anyway, the number here is 21%. If you do the math out, what is oxygen's contribution? What is oxygen's contribution to atmospheric pressure? Oxygen's contributions to the 760 are 159. And why don't we just round that up to 160 just to make the number easy to work with? So 597 plus 160 or 159. And we happen to see some other stuff, carbon dioxide and water. And I actually don't really want to talk about those at all because for what we're doing, they're not super relevant for right now. But if you want to rework the slide here, I threw in a little bit of water, some of this water vapor, and a little bit of carbon dioxide as well too. So yes, those contribute a wee bit to that 760 number. So if you add up all these partial pressures, we should get 760. And there's the number 760. There's the number 760 right over there, okay? So now 21% of 760 is 160, all right? So what I want you to see then, this is atmospheric pressure. The second part of the table is looking at the partial pressures within the alveoli, and I'm going to get into that in a separate lecture because what we'll see then, the partial pressure of oxygen in the alveoli is something of great interest to us. How does exchange occur? You create a pressure gradient, and I'm showing you where we're deriving these pressure numbers for oxygen to begin with, all right? Okay, so now let's look at something else. And okay, I'm going to be honest with you. Right now, I've just done a little bit of math without actually showing you the math. I'm just giving you a number, that's 760, and saying that there are different gases, each of which contribute to add up to that 760. And I showed you a table with some of these numbers. And I understand if there's a part of you that feels a little bit like, oh my gosh, here's a table full of numbers. He's telling me all I need is the 160 that I need to know, as well as the 760. And 21%, okay, I don't understand. To what end? Why do we care about this at all? Well, just to give you a preview for where we're going with this, is this. These are the three exchanges, right? From the atmosphere out to the lungs, exchange number one, lungs into blood, exchange number two, blood into tissues, exchange number three, right? These are the three big exchanges that we see. And how does stuff move? How does gas move? According to a pressure gradient. And where is that pressure coming from? Well, look, the inspired air or atmospheric air, the PO2, partial pressure of oxygen, is 160. Where did we get that number 160? We got that number knowing that how much oxygen is here in the atmosphere. It makes up 21% of the different gases out here. We know atmospheric pressure is 760 at sea level. 21% of 760 is 160 or 159. And so that's why we care about that, because in a future lecture, we're going to go into the PO2 of atmospheric air, and that's 160, because all we care about is oxygen. Remember, when diffusion occurs, the diffusion of a given substrate, that substrate only cares about gradients for that substrate. That gradient, the substrate only cares about moving down a pressure gradient or a concentration gradient for that substrate alone. And so that's why all we really care about is PO2. What is the PO2 of the lungs, out the alveoli? It's 104. Where did that number 104 come from? Well, we see it, whoops, where's that table? Wrong table. We see it right over here at PO4. And this we're going to have to explain. Why is the PO2 in the lungs lower than PO2 in the atmosphere? Well, first off, thank goodness it's lower, because now what do I have? I have a pressure gradient, right? 159 here and 104 here. Which way is oxygen going to move? Oxygen is going to move according to its own pressure gradient, meaning the partial pressure is greater here for oxygen than it is here for oxygen. So that's why oxygen is going to come into our lungs. That's exchange number one. In any case, again, a lot more detail on this in a future lecture. The only reason I skipped ahead here was to impress upon you that that's why we're going through that whole thing of 760 is atmospheric pressure and 160 is the PO2 in the atmosphere, because it's relevant. Down the road, it's relevant. Okay, so then the next thing that I want to show you is humidity and temperature affects partial pressure. This for those of you, well, all of you who are watching or in my class, you don't need to know this for your exam. I just need you to understand true or false. Humidity and temperature affects partial pressure. And the answer there is true, and that's good enough. This particular table shows you the partial pressure of a gas in dry 25 degrees Celsius air versus in 100% humidity versus in warmer air at 100% humidity. And you'll see how the partial pressure of oxygen diminishes, and it goes from 160. Again, where did that 160 come from? That 160 came from right over here, right? 21% of 760. And so here it is at a nice comfortable humidity level and temperature is 160. But then when it gets pretty darn humid and warm, the partial pressure goes down. Now already, what does that mean? Who cares? Well, the reason we care about that is now the PO2 is lower. Okay, if the PO2 is lower, remember this thing? Instead of 160 to 104, it's now 150 to 104. Do I still have a gradient? Yep, I still got a gradient. Is the gradient a little less steep and significant? Absolutely. So what? Why do we care about that? Well, a ball will roll faster down a steep hill than it will down a not very steep hill. The rate of diffusion will be greater, the higher the gradient, or the more significant the gradient, compared to a low gradient. And so 150 to 104, it's still a good enough gradient for us, but my point is the rate of diffusion in and of itself will generally be diminished, which is why it can be harder to breathe in hot, humid air. So again, you don't need to memorize these numbers. I just need you to know true or false, humidity and temperature affects partial pressure. 100%, absolutely, yes, it does. Now, the last part here is describe a few different ways to interfere with PO2 in the lungs. And this might actually be better served in a future lecture. But if this is the PO2 in the lungs right over here, what are some ways that we can actually mess with that? How can we interfere with the PO2 in lungs? Well, here, this is a normal lung. PO2 is normal. If you have emphysema, then you're not getting quite as much, you actually have a loss of lung tissue. So the PO2, it might be normal, or it could actually be on the low end. If you have various fibrotic lung diseases, PO2 might be normal or it could be a little bit low. Pulmonary edema is showing you a bunch of swelling. So even though you're getting air in just fine, there's too much of a gap here for oxygen to adequately diffuse. But probably the most famous case is something like asthma. Something like asthma, the bronchioles themselves are constricting for various reasons. And when that happens, you can't get quite the air in that you want. And so the PO2 itself will be low. So the reason I have this question here, how to mess with PO2, and again, really what I meant here is PO2 in the lungs, and that's what is in your learning objectives. But eventually what we want to understand is also, well, how do you get lower PO2 in the blood? And this same picture is showing you some of that. PO2 is low here, PO2 is low here, PO2 is low, PO2 is low if you have some issues. Either you have swelling, so there's too much diffusion distance, or you don't have enough oxygen in the lungs. Well, then if you don't have enough in the lungs, there's not going to be enough getting in the blood. If you have a fibrotic lung disease, something that we've talked about in previous lectures, then you've got normal oxygen here, but the walls are too dang thick to actually get into the blood itself. And so there's various ways or mechanisms by which PO2 itself can be messed with or interfered with. And so where we're at right now, we described the approximate percentage and partial pressures of the major gases in the environment. What were the major gases? Nitrogen and oxygen. And of those two, 21% is oxygen and 21% of 760, which is atmospheric pressure, is going to be 160 millimeters of mercury. So that's the key thing here. What is partial pressure? Partial pressure is the contribution of a given gas toward total atmospheric pressure. That's what partial pressure is. So remember that oxygen's contribution, oops, wrong table. Oxygen's contribution is 159, 160. Nitrogen's contribution is 597. And then carbon dioxide and water are pretty small when you look at those contributions, but they should sum up to 760. And then we looked at very briefly, not in a lot of detail, because a lot of that detail is more for clinical conversations, but a few different ways to interfere with PO2s in the lungs. Maybe we didn't really say a few. Probably the main thing here is bronchial constriction or bronchoconstriction. Okay, so that'll wrap it up for this particular video.